Okay, so we are back to videos. Well, I mean, videos with me. Um, the previous video, what I showed you was how you could use some software to solve a least squares problem. And what I want to go over now is the mathematics behind least squares problems. And we're just going to start looking a little bit at this because, um, again, this is a video that can't be too long, and I'll finish my considerations and I'll do a few worked out examples by hand in the next video. So for now, what are least squares problems? We saw, but how do you solve them mathematically is the next question. So um, I'll remind you that a least square problem in the way we formulated it to that point is you have a collection of data points x1 to xn, y1 to yn, well, I mean, x1, y1 to xn, yn, and you want to find the coefficients a and b of the line y equals a plus bx such that the norm of the error vector is minimal, where y tilde that's used in the computation of this norm here is given by evaluating the value of the function y equals a plus bx at the point x equals xi. Okay? So, by the way, before I go any further, notice that I've adapted the notation compared to what I was showing you earlier. Here I'm using y equals a plus bx instead of y equals ax plus b. But I really want to stress that this does not change anything. What it does change is the order of the columns in the matrix that we deal with, but that's minor as a problem, okay? So what we did in the previous video was to solve this problem by using a genetic algorithm. And I showed you that you get a solution that is quite close to the one I had guessed by luck. Okay, so this is one way to do it, but I'm going to show you now how to do it, let's say, properly. And by that, in a way where we know the solution to be exact as given by a given method. Okay, so I have my data points, and for a given data point, I, then the epsilon I, the error that I make, is y minus y tilde I, okay? And if I replace y tilde I by the value that it really takes, because it's given by the function y equals ax plus b, a plus bx, you see I'm already making the mistake again. Just in passing, in France we always write ax plus b. In North America you write a plus bx, and that's, I don't know why these things happen, but okay. So I might say ax plus b when it's written a plus bx, but as I said, all that changes is actually at the bottom of this page here. So forget this. What's important here is you can write the error at all the data points in the same way as we have done. Okay, so epsilon 1 is simply the abscissa of the data point, y1, minus what it is given by our approximation, so a plus bx1. And all the way down to epsilon n is yn minus a plus bxn. We can write this in matrix form. Okay, so I'm going to write that E, which is our error vector, which is simply that vector of epsilons, is B minus AX. B here is the vector of Y's, and A is the matrix that has the coefficient in front of A in the first column, and the coefficients in front, well, I mean, in this case it's after, but it doesn't matter, the coefficients of the b's in the second column. And you see what I was saying earlier. If instead of writing y equals a plus bx, you wrote ax plus b, what would happen is that the x's would be in the first column and the ones here would be in the second column. But that's the only difference, okay? And finally, x is, of course, our unknowns, and in this case, it's a and b. So let me reformulate the least squares problem once I've done this. Let me consider a collection of data points x1, y1 to xn, yn, a matrix A that I'm going to take as having m columns and n rows, which is not the notation we have in the past, but this is a definition, doesn't really matter, okay? The important thing is A has the same number of rows as the vector B here, okay? We call a least square solution of AX equals B a vector x tilde, and this one is in Rn, okay, so the same number as the columns in A. So we call a least square solution a vector x tilde in Rn, such that for all other vectors than this particular vector, this least square solution, so for all any other vector in Rn, I have that the norm of b minus ax tilde is less than or equal to the norm of b minus ax. So remember what we just wrote. B minus ax tilde is okay, it's the error that you make. Okay, so so if I find a point, okay, so this is at any point, but if I find a point x tilde such that for this particular one, the error is less, we could call it E tilde, okay, the error for x tilde. The error is less than the error that you have for any other vector x, then you have a least squares solution. Okay. I need to be mindful of the time. I will break whenever we get to the point where I have to break. Now, to solve this this problem, the least squares solution problem, we need these two little tools. So the first one is what is called the best approximation. And I am not going to show you this result, to show mathematically this result. I am just going to present it to you and the best approximation theorem. Okay, so the best approximation is essentially what we just said. So if we have a vector space and we take a subspace W in this vector space and a vector in the original vector space, the best approximation to that vector in the subspace, so be careful, so the vector we take in the original space, but our best approximation is taken in the subspace. So that best approximation is a vector v tilde, and it is, of course, in the subspace in which we are trying to approximate. And that vector v tilde is such for any other vector w in the subspace that is not equal to v tilde, the norm of the difference between v and v tilde is less than the norm of v minus w. Okay, and that's what we call a best approximation. It might be a little hard for you to wrap your head around what that means, but don't pay too much attention, okay? This is a sort of theoretical definition. And then there is a theorem, which is that theorem here, the theorem 4 here, that tells us the following thing. If I have a vector space with an inner product, and we have seen the dot product, which is an inner product, I'm not going to go into the details. For those of you who will or have taken Math 2090 will see what an inner product space is. Just understand that these are, I mean, the type of spaces we're working on, Rn, for example, are inner product spaces, okay? So if we have a vector space that has an inner product, and we take a subspace of that vector space and a vector in that vector space, then the projection of V onto W is the best approximation to the vector V in W. Okay, so if we want to solve the best approximation problem just above definition 3 here, we can use this, and we know that using the projection of V onto the space W is going to get us that best approximation. And I think I'll stop here and I'll continue in the next lecture.